All right, the last example we're going to do from 15.2 is example number 3. These two examples get a little bit harder, so hopefully you've practiced your first couple examples and you're at least a little bit comfortable with U-substitution. But looking at example number 3a, I noticed that if this were a derivative problem, this would be a little bit of a chain rule piece in here, and so that's my red flag, my clue that I might be using U-substitution. Just like before, what do you think we're going to call U? That's right, I called U 1 minus x, so then the derivative would be negative 1 dx, right? The derivative of 1 is 0, the derivative of negative 1x is negative 1. Okay, so now that I have that, I'm going to go back in. I'm going to rewrite my problem, and instead of with a square root, I'm going to call him a quantity to the 1/2. And I'm going to take out all this stuff, and I'm going to use my U substitution. So instead of calling him 1 minus x, I'm going to call him u to the 1/2. I want a du in there, so I need a negative 1. So are you okay if I put a negative 1 here so I can call that du? As long as I, remember, balance it out with a negative 1 in the front. So then I'm going to take out this negative 1 dx, I'm going to call that du, and then I have the negative 1 in the front still from before. So all of this is gone, all of this is gone. Uh-oh. Don't I still have an x in there? In all the problems we've done in the past, all of our stuff has been able to be substituted in by u or du. We might have had to balance out with a constant and balance it out with a 1/2 or a 1/3 in the front. But we have an extra x in this problem. And unfortunately, we can't just go through and divide stuff by x and get rid of it. I wish we could do that. That'd be easy. But we can't. And so we have to somehow get this x away, or at least call it in terms of u's, so that we have one variable only, not x's and u's. So we have to somehow figure out how we can write x in terms of u. So here's what we're going to do. Do you remember this equation that we said up above where we said u equals 1 minus x? Can I resolve that equation and get it to say x equals? Can I move the x over, move the u over? Can I solve and say that really x is the same thing as 1 minus u? So take that top equation and solve it for x instead. So now, instead of my problem saying x right here, could I call it 1 minus u, because that's what x is equivalent to? I still have the u to the 1/2, and I still have my du. But now, at least look, how many different variables do I have? Now I just have the one variable. Now this is still a product rule, so I can't really do antiderivatives yet. I still need to manipulate this problem a little bit to make it look like a antiderivative rule I do know. So what I'm going to do now is I'm going to distribute the u to the 1/2 through. I'm going to distribute the u to the 1/2, and I get u to the 1/2 minus, what is that, u to the 3/2. Remember, when you multiply, you really add the exponents. And so now this looks like an antiderivative problem that I can do because I have power rule. So I have a negative 1 in the front, and remember that negative 1 is to everybody. So I'm going to use big old brackets to remind myself that that negative 1 has to go to every single term. I'm going to use my power rule. I'm going to add 1 to the exponent and divide by the new exponent. So I have u to the 3/2 divided by 3/2, aka multiplied by 2/3, his reciprocal. I'm going to add 1 to the exponent, so I have 5/2, and I'm going to multiply by his reciprocal 2/5, and then I have my constant of integration at the back. Remember, this negative 1 goes to everybody, so I'm going to then distribute it through. I have a negative 2 u to the 3/2 over 3 plus, because I distributed the negative, 2 times u to the 5/2 over 5 plus c. Remember that my last step is going through and back substituting in what I called u, which was the 1 minus x from the beginning. All right, a little bit harder, right? Because we had this extra x in here, we had to take my u equals equation and solve it for x instead, and then substitute in an additional time so that we have this 1 minus u instead of x's. We have our u to the 1/2, and we have our du, making sure that our antiderivative problem, our integral here, is all just in terms of one variable. Okay? All right, let's do another one over here. So it looks like I have another kind of similar example. What I'd like you to do is pause the video and see if you can do this example all the way through now that you've seen example number 3a. All right, I called u 2x minus 1. The derivative then is 2 dx. So it looks like here I took my original problem, and instead of calling it the square root, I changed it into that rational exponent of a 1/2. I then took my problem and I substituted in what I have. I had here, instead of 2x minus 1, I called it u to the 1/2. I needed a 2 dx, so I can put a 2 in here and call that du, but I needed a 1/2 to balance it out. So I have my 1/2, I have my du, I have my u to the 1/2, but I have this extra x right here that had no other substitution pieces for it. And I don't know about you, but I don't know how to integrate if I have x's and u's, because we don't know implicit anti-differentiation yet. So we have x's, we have u's, and we have to somehow get that x into terms of u's. So I'm going to use my u equals equation, and I'm going to solve it for x. I'm going to add 1 to both sides, and I'm going to divide by 2, and I end up getting that x is really u plus 1 over 2. Did you get this far? All right, so instead of calling him x in my original problem, I'm going to call it u plus 1 over 2. So now your indefinite integral should look like this. You still have your 1/2 from the beginning. You have your x, which is now u plus 1 over 2. You have your u to the 1/2, and you have your du. So now you have all u's in your problem. Okay. From here, we've got to make it look a little bit nicer. I have a 1/2 out in front, and I don't know if you noticed this, but this is really a 1/2 here, and I'm going to take that 1/2 also out to the front. So if I already had a 1/2 and I brought another 1/2, now don't I have a 1/4 out in front? That leaves me then with this u plus 1 times my u to the 1/2. Okay, so again, I want you to notice here, this pink, I have a 1/2 right here that I'm going to bring out in front. And I'm allowed to do that as long as it's just a number, right? So I already had a 1/2. I brought another 1/2 out. That gave me a 1/4 out in front. I had left over this u plus 1 times my u to the 1/2. I'm now going to distribute my u to the 1/2 through, giving me a 1/4 times the indefinite integral of u to the 3/2 plus u to the 1/2 du. I now have two different terms separated by a plus sign, and I can use my power rule now. Add 1 to the exponent and divide by that new exponent. Remember that 1/4 has to go to every single term, so I use big old parentheses or brackets to let me know that I needed to distribute that 1/4 through eventually. I added 1 to my exponent, I multiplied by the reciprocal or divided by that new exponent, and you should get this. My last step is I'm going to distribute this 1/4 through and resubstitute or back substitute in whatever I called u in the first place. When I distributed the 1/4 and I simplified, I ended up getting 1 over 10 and then 1 over 6. I'm going to resubstitute in what I back substitute in what I called u, which was my 2x minus 1. So your final answer should be this. You should have a 2x minus 1 to the 2/2 power all over 10, plus a 2x minus 1 to the 3/2 power all over 6, plus c. I know those were kind of complicated, so you're going to have to practice. Go through that video one more time or 2 more times if you need to. I'd like you to try it first, then see if you're getting the same answer as I do. Let me know if you have any questions. I'm here for you guys, okay? I also wanted to let you know that we are not doing example number 4, so don't worry about that last one. Just worry about your U-substitution pieces